Slide 1. Today, we thoroughly analyze the future of semiconductor power delivery, the structural revolution of 2026, brought by BSPDN and the Japanese winners. In 2026, chip structure will undergo its most dramatic change in 50 years. That is BSPDN, Backside Power Delivery Network, moving all power wiring, which was previously on the front, to the backside of the wafer. Without this Copernican turn, miniaturization beyond 2 nanometers is impossible. Intel, TSMC, Samsung, behind this technological race, where the world's 3 major foundries are betting their fortunes, did you know that Japanese companies like Tanaka, Kikinzoku, and Fujimi Incorporated hold the indispensable keys? I will unravel the backside revolution that investors are overlooking with dense original analysis. Slide 2. Why now? The power-hungry AI crisis. First, why is it necessary to make a massive investment to move power? To the back now? The reason is clear: the evolution of generative AI. Latest AI chips, including the successors to Blackwell GPUs, have become power-hungry monsters that simply cannot operate with traditional power delivery. With thin front-side wiring, attempting to flow the necessary high current causes overheating and voltage drops. This prevents computational performance from being realized. BSPDN is not just a miniaturization technology. It is an essential infrastructure to keep AI evolution from stopping. Slide 3. The battle of giants: Intel versus TSMC versus Samsung. A 3-way battle has begun over this new technology. Intel leads the way. With technology called PowerVia, they aim to start mass production, ahead of competitors and regain technological leadership. The reigning champion, TSMC, will introduce even more advanced technology, called Superpower Rail, in the A16 process in late 2026. This is the ultimate structure that flows electricity directly to the base of the transistor. From the back, maximizing logic density. Samsung is also chasing hard towards 2027, making 2026 a turbulent year where these new technologies intersect. Slide 4. The material shift from clogged copper to flowing ruthenium. The introduction of BSPDN is also a revolution in materials. Copper, which has been the protagonist of wiring until now, is useless for fine backside wiring. So molybdenum and ruthenium become the protagonists. Imagine this: if copper is a water hose, it has become so thin that it is clogged. In contrast, ruthenium is a super material that allows electricity to flow smoothly, even when extremely thin. From 2026 onwards, the blood vessels of semiconductors will evolve from copper to ruthenium. Slide 5. The king of precursors: Tanaka, Kikinzoku, and Adeka. So who can supply these new metal materials? This is the sole stage for Japanese companies. Tanaka Kikinzoku Kogyo of Japan holds the world's highest technology in liquid raw materials, precursors, for filming ruthenium. The material they developed, Trust, has the world's highest vapor pressure and is said to be a unique solution, enabling stable mass production. Also, Adeka leads the market in the synthesis and purification technology of high dielectric materials and ruthenium. The more new wiring technologies spread, the higher the dependence on them becomes. Slide 6. The process. Flip, bond, grind, reveal. The process of making BSPDN is also extremely unique. Flip, bond, grind, reveal. Flip the wafer, stick it to a glass carrier. Substrate, grind off the silicon from the back and reveal the transistors. Here, the wafer is ground down to a thickness of just a few microns, thinner than a hair. Supporting this extreme thinning process are Disco's grinders. Without their equipment, which holds 80% of the global share, this process cannot be established. Also, Tokyo Electron shows overwhelming presence in bonder equipment that bonds wafers uniformly without bubbles. Slide 7. The polishing master, Fujimi Incorporated. After grinding, the process of smoothing the surface in nanometers and exposing the electrical path TSV is CMP. What is important here is the technology of Fujimi Incorporated. They provide specialized high-selectivity slurry. This doesn't just grind, it distinguishes the hardness difference between silicon and the insulating film, stopping exactly at the target layer. If you grind too much, the chip breaks. If you don't grind enough, electricity won't flow. It is this godlike control technology that determines the yield of BSPDN. Slide 8. The overlay nightmare Canon and Nissan Chemical. However, there are challenges. The biggest wall is distortion. When wafers are bonded and ground, mechanical stress causes the wafer to warp. It is extremely difficult to align the exposure perfectly, with the circuit on the front side on that distorted backside. Canon has built a unique position here with their measurement device MS-001. that maps distortion like a fingerprint. Also, to prevent distortion in the first place, temporary adhesives that bond strongly, but peel off cleanly are essential. In this field, Nissan Chemical and Shin Etsu Chemical provide special materials that can withstand high-temperature processes, supporting the foundation of manufacturing. Slide 9. The thermal wall and cooling costs. Another critical challenge is heat, grinding away the silicon substrate risks, raising the chip temperature by 15 to 20 degrees. This is not just a problem of chips breaking. For data center operators, it means cooling costs will skyrocket. That is why thermal TSVs and high thermal conductivity, insulating materials become important. The performance of TIM thermal interface materials provided by Shin Etsu Chemical will be the key to determining the operating costs of AI servers. Without the materials from these Japanese chemical manufacturers, AI servers would go down from heat, and indeed could not even be manufactured in the first place. Slide 10. Investment conclusion. Bet on the enablers. In conclusion, in 2026, the transition to BSPDN will shift the center of gravity of semiconductor manufacturing. From lithography to back-end-like processes, Intel, TSMC, Samsung, whoever wins, there are technologies that will definitely be used. Behind the scenes, Tanaka Kikenzoku's ruthenium, Fujimi Incorporated's high-performance slurry, Disco's processing equipment, Tokyo Electron's bonders. They are the enablers supporting this huge technological transformation as stagehands. Behind the news of glamorous chip makers, the technological power of Japanese companies challenging the limits of physical laws will be the protagonist of the next growth story.